So, good morning, guys. In this video, we're gonna design a multiplier using a data path and a control path. Okay, till the last video, we designed a circuit. So, we designed machines, finite state machines. So, in that, we only had one module, right? But here, for complex machines or complex digital system, we generally divide the hardware into two: data path and control path. So data path is a module in which there all the functional units: adders, multipliers, subtractors, counters, and the values and the registers are stored. And control path is a functional unit. Control path is nothing but a finite state machine that provides control signals which activates the data path. So we can design any complex digital system into two: control path and data path, right? Data path is actually act as a memory which store all the adders, subtractors, operands, and it store back the result. And control path gives the control signals which activates the data path or memory at different times. Okay, so here in this example, we are gonna design a multiplier, a 16-bit multiplier using control path and data path. So we can look at the code. Okay, this is the code of the multiplier circuit. See, first we defined a module name multiplier data path, and we give our output signal as EQZ, LDA, LDB, LDP, clear B, decrement B, data in clock. So, what are these signals? Let's look at that diagram first, right? So, this is the flow chart of the multiplier. First, we need to start, then we need to input two values, A and B. Then we initialize a register P at 0. And what happens? We add the A value to the P, which was initially 0. How many times we add? B times. So you know that multiplication is an repeated addition. That means 4 into 3 equal to 4 plus 4 plus 4, or 3 plus 3 plus 3 plus 3. Okay. So addition, repeated addition makes the multiplication. So that same logic we are using here. We add a times, we add p equal to p plus a. How many times? B times. At the each time you carry out this operation, b get decremented. And when b equal to 0, you can stop this operation. Okay. So first we design a control path and a data path. So this is the control path. First, we input the data to the bus. You know that bus are channels or interconnections made inside a hardware. You can see buses inside a CPU. There are different buses: address bus, data bus, control bus. Address bus mainly transfers address of the memory locations, while data bus fetch the data. Control bus actually used for transferring control signals, right? So you input the data, that means the A and B, that is the data here. You input A first, then A goes to the A register, and after a delay you input the B here, so B goes to the B register. Then what happens? Then the A is loaded to the adder, and P, which was initially set at 0, was loaded to the adder, and A P equal to A plus P. So the result will be stored in P. Okay. At the same time, B will be decremented and compared with 0. B equal to 0, then we need to stop. So you can see so many signals here. Load A, which enables the loading of A from the bus to the register. Load P, which enables the loading of the P from the adder to the P register. Load B, you can see clear P, which sets P equal to 0. You can see decrement B, which decrement the value of P. can see EQ is said here, that makes, can see EQ is said here, that is equal to signal that is given as an output from the data path. So these four five signals are input. You can see it is point towards the data path, while EQ is an equal signal which is pointed outwards to the data path. Okay. So now let's look the control path. Control path, you need to generate these signals. These five signals you generate in control path, right? So you can see in control path we need to initially start, then we need to load the A register with the data input, then we need to load the B register in the data input. At the same time we clear P, then we add P equal to Z, that means P equal to P plus A, and you decrement B, you check B equal to 0, and if done, yes, right? So you divide these stages into four stages, right? And you can see in the S3 there is a loop. What means that loop is this: if P equal to 0, then you jump to S4, or else it will get decremented. That means a repeated addition take place here, right? So you can see, yeah, this is the correct diagram. You can see, control path generates load A, load B, load P, clear P, decrement P signals to the data path, while data path in turn also generates a signal which is EQZ to the control path, so that the control path can generate the final signal that is called done. Start and data in and clock are provided by the user, right? So you can see that that's the definition of a data path and control path, and we're going to design a multiplier using data path and control path. See, initially we declare a module named data path. You can see EQ is the output, load A, load B, load P, clear P, data in, all are inputs. And data in, we know we are designing a 16-bit multiplier, so you give a data in as 16-bit. You have declared some values x, y, z, bus, b out, all are 16-bit, and you assign data into bus. Initially we need to load that. See, this loading, yeah, data in is load to the bus, that is given as this statement: assign bus equal to data in. This is an important statement. I didn't find these statements in some of the codes here which give you an error, right? And then we're gonna load, and we're gonna declare more variables or more modules. PIPO means parallel in, parallel out shift registers. That is for loading A. That means, you see that this module is declared here. Data in is input. That means now the data in is in bus. So you load this bus, or you load this data in to the A register which is declared here as Z. Okay, no, X. Okay, so you input bus, you there comes a load signal, there is a clock, and you assign the value which is in the bus to the A register which is named here as X. See, this module is declared here: input load, input clock, output data out at the positive edge of the clock. If load is active, if load signal from the control path is active, then you take data in and give it to data out. That means, this means nothing but the loading of value of A from bus to the register A. Register A is given here as X. Similarly, you need to load B, but the difference is here B need to be decremented at every operation, right? So instead of giving PIPO, you define B as a counter, right? You define B as a counter which have a data input, load signal, which also has an additional decrement signal. If decrement signal is active instead of load signal, then the data output is decremented by 1 unit. Okay. So the next register you need to look is PIPO2, that is the P register which has an additional clear P signal. So you can look at that when the clear P signal is active, irrespective of the data in, the data out becomes clear. That means the data out is 0, 16-bit 0. You can see another module add. What does add do? Add simply adds two input datas, input 1 plus input 2, X which is A, Y which is P. So you can see Z equal to A plus P, and there is an equal module which compares b with 0. You can see that here, equal to module which inputs a data which compares that data with 0. Okay, so you know that we have successfully explained the data path. Now let's look at the control path where this load a, load b, clear b, decrement b, all that signals are generated, right? Okay. Okay, let's look at the module control path. This time scale means it's giving an precision, right? Okay, you can see that the module control path which have an output as load a, load b, clear b, decrement b, done, and an input we give user give the input as clock and start. EQZ is given from the data path. It is also an input signal. So you declare three states. We named here, we divided here control path into four state: S0, S1, S2, S4. That is declared here as parameters with a specific binary value, right? So at post edge of clock corresponding to state, if it is in state S0, and if the start signal, we user gives the start signal as input, then it jumps to S1. If it is in S1, at the next clock it must jump to S2. If it's in S2, at the next clock it must be jump into S3. And if it is in S3 and the B is decremented to 0, only then it need to jump to S4. S4 is the final state. Okay. Initially or default we set a state at S0. So that's only the case of states. Then we're going to define each state. At S0 all the signals are 0. At S1 you can see here what is the S1, you can see there is data in loaded to a, so you need to make data in, so you need to make load a active. In S2 you need to make load b and clear p active, and in S3 you need to make decrement p and load p active. Okay, so we write like that: load a is initially all are 0. At S1 load a becomes active. As S2 load b becomes active, clear p becomes active. S3 load p and decrement p becomes active. S4 only done become active, else signals are 0 by default, or signals are 0. So only this much. We declared a control path, we declared a data path, and we divided data path into multiple submodules, right? Then we can look at the test bench. Okay, initially we declare test bench, and inputs you declare as register and output you declare as what, wire. So you have many wires here, right? Multiple, you call the module as dp, you call the control module as con. Initially you give clock and start bit, after 3 bit, after 3 seconds you make start bit active. Simulation is carried out for 500 seconds. You give negative edge of clock at every 5 seconds, and you give the data in 17, and after 10 seconds you give another data in 5. This is a, this is b. Okay, and you print dp dot by. Why? Here you can't see the output, only you can see the output in the inside module of the data path. You know that in data path, when you take the code for data path, you can see that inside data path you declared y, that is our output, that is the result of our operation. So in order to call that y you need to use this way of calling. It means dp means the data path declared here dot y. Okay, dump the file to mul.vcd, you dump the variables, all variables of test bench and then end module. That's all. So let us simulate this one. Oh, sorry. I Verilog minus O multiplier, and the name of the multiplier dot v space multiplier slash test dot v. Okay, test dot v. Let's copy that, right? Test no such file or multiplier test. Okay, okay. I don't give such dot v, right? Okay, there is no error. So, in order to see the output, you should give vvp space the object file name, which is multiplier, right? Okay, see, you can see 0 first. We given the values are 17 and 5, right? So you can see at first the 17 is loaded, then 17 is added with again 17, 17 into 2, 17 into 3, 17 into 4, and finally the 17 into 5. This was our done signal which become active at the final computation. So we have successfully implemented a multiplier using data path and control path. This form the basics of designing a microprocessor. You generally model any hardware into two. It's a data path and control path. Okay, so thank you.